Hey everybody, we're in Notebook 12. We're going to talk about sampling distributions and the central limit theorem, and this is why statistics work. We're going to kind of connect the probability to the statistics here today. So, sorry, go ahead and get Notebook 12 open, which is sampling distributions and the simple limit theorem. And what is a sampling distribution? Well, sampling distribution means that we repeatedly draw samples of the exact same size from a population. And it turns out that when I do this, the averages from the samples will have a bell-shaped distribution, which is centered upon the mean of the population. Okay. Why? Well, we want to estimate the mean. A lot of times we don't know the population mean and we want to estimate it. So what do? Well, then we can repeatedly draw samples of the exact same size, calculate the means of those samples, and we're going to get a bell-shaped distribution, right? And the center of which is going to be right at the average for the population, the mean for the population. So let's watch that in action today. That's what we're going to do. So we have this huge table called united.csv, and the delay column is the number of minutes delay for each flight in the table. And so again, we have thousands of flights in this table. And so we can ask the question, what's the average delay? And again, what we want to do is we want to repeatedly take samples of the same size, take those averages. We'll get this bell-shaped distribution. And when we get better and better, the bells are going to be narrower and narrower. Why? Well, that will provide a better and better estimate, right? If the bell gets narrower, which will happen as we do this more and more often, we get a narrower and narrower bell, so we'll get a better and better estimate of exactly what the average is. And this is why statistics works. Okay, so let's jump into our notebook. And here is this ginormous table. Okay, and they've got all of these flights from 2015 and the flight numbers and the destinations. And I don't know all of these. I know STL is St. Louis. I would guess that SEA is Seattle. So an HNL, I believe, is Honolulu. So we've got these flights from all over the world, and we know how long they were delayed for, the number of minutes. Okay. So what are we going to do? We're going to use our dot sample method. So what are we going to do? X is equal to united.sample 100. And so it takes 100 random rows out of the table united. And then we're doing dot column to get an array of what? Well, the delays. So we grab 100 flights at random, and we have the delays. So X is an array. We take the average of X, and the average minutes of delay for these flights was just less than 13 minutes. Okay? And then we're doing all of this at once. So instead of having 3 lines of code, right, here we do it all at once. And notice that we get a slightly different thing. Why? Well, because this is a different sample, right? Every time we run the dot sample method, it re-randomizes. So when you run all of this, you are going to get slightly different things. Sorry, I was rerunning these, and they'll be close, but they won't always be identical, right? Why? Because every time I run dot sample, it is going to change slightly based on which 100 rows got picked at random. And it'll be a slightly different 100 rows every time that I resample. Okay, so the sampling distribution, look at this, okay. We're actually importing the sampling demo. Why? Well, take a look, okay. So suppose we have a uniform distribution. Now, uniform distribution, we learned this in probability. This is like the dice rolling distribution, right? Where every outcome, the reason it's flat across the top is because every outcome is equally likely. Okay, that's a uniform distribution. And here, when we took samples of size 5 and then took the mean, we get something that's reasonably bell-shaped. And at size 10, it's pretty good bell shape. And what's going to happen as we do sample sizes that are larger and larger, the bell gets better and better. So first thing is, the law of large numbers says that this estimate that we're trying to find is going to be a better estimate if the sample sizes are larger. Okay, so the second thing we're going to do is we're going to look at this distribution, and it's symmetric, but it's not uniform. All right, so that's what this part is saying. Hey, we're going to have this sort of anti-bell shape. And Lynn, look at this. Even with sample sizes of only size 3, we're already seeing a bell shape. It's not as clean as the other one where we started with uniform distribution. But notice as the sample size gets bigger, right, and we get up to these sample sizes of 30, we're getting a very good looking bell shape. Is it perfect? No, it's not perfect, but it's getting to be very good. All right. So moving down, what's the next? What about a distribution that's very wacky? Okay, so we don't have a bell-shaped distribution, and it's not symmetric. It's sort of like a half bell. We've got this sort of ski jump look to our distribution here. And again, even at size 3, we're starting to see a bell shape emerge. It's cut off here on the left. It's not fully formed, but you'll notice the same thing. And this is the demonstration of the law of large numbers. Again, when I get to these larger samples, now here I'm getting a little bigger, right? Because we only had size 30 before, and now we're up to size 35 and then size 100. But look, even though the original distribution was not bell-shaped and not symmetric, we get a very bell-shaped, very symmetric looking histogram when we take a sampling distribution and when the sample sizes get larger. Okay. So here is a normal population. So this is the population is standard excuse me, the population is bell-shaped. So of course all the sampling distributions are also bell-shaped, and we get a cleaner looking bell when we have larger sample sizes. Yes, that is true. Okay. And then the sorry. The notebook just asks us, what are we supposed to observe in the graphs above? And it's some of what I told you before, right? As the sample size goes up, right, the sampling distributions begin to approach the normal distribution, so it's bell-shaped. Okay? And the sampling distribution, regardless of the original distribution, even when it was sort of the anti-bell or when it was, the ski jump, it didn't matter what the original distribution was, the result of the sampling distribution always turned out to be bell-shaped. And then, did you notice the x-axis keep changing? And you can go back, you should do this. It turns out that the x-axis gets shorter and shorter, right? So it turns out that even though the bell curves were produced on the same size graphs, the graphs were labeled differently. Why? Well, because the amount of x-axis was less and less, right? The bells are actually getting narrower and narrower. So the bell might be more normal early on, but as the sample size increased, the bells were getting taller and narrower. Still bell shapes, but the second one produces a much more accurate estimate. Okay, so that's what they're looking for you to understand there. And again, read this and understand this. It's what I've just said. All right, and then the law of large numbers, again, as the sample size increases, and when it's very large, you can have some confidence that the average is pretty close to the population average, okay? And again, we can quantify that, but let's just say when we use a large sample, we get a pretty accurate estimate. And all of this goes into the central limit theorem. Okay, so again, what are we looking for? Notice that the center of these bell shapes is getting closer and closer to the average, and the width of the bell is getting narrower and narrower, so that the estimate is getting better and better. All right, and let me get rid of the ink. Okay, I told you about the law of large numbers. The central limit theorem says that every single sampling distribution will have a bell-shaped distribution with the same mean as the population average, and the standard deviation is the standard deviation of the population divided by the square root of n, which makes it clear that since n is in the denominator, as n, the sample size, increases, right, then the standard deviation or the width of the bell is decreasing, right? So as sample size, since it's in the denominator, as sample size gets bigger and bigger, the standard deviation gets smaller and smaller, so we have a better and better estimate. Cool, all right. And so you can see these are the quartiles. So the 25th percentile is between green and blue, and the median or the 50th percentile is between blue and orange. And the 75th percentile is the vertical line there between orange and red. Okay, so this is the result of the central limit theorem. Everything turns out bell-shaped, which is why we can do this statistical wizardry, right? And so here we go with a large random sample. All right, and we're looking at the population distribution, which is not exactly bell-shaped. It's skewed to the right, massively skewed to the right, hardly bell-shaped, a little evidence of bell-shape. And so now the population average is 16.65 minutes. And when we take a sample of size 10, right, again, these averages are going to be close to 16 and 2/3. 16 minutes and 40 seconds, but notice they jump around a good bit, right? Well, this is what happens when we use, here we're doing 1,000 iterations with sample mean size 10, and notice that we're starting to get a bell shape here, all right? And then with a sample size of 50, you'll notice that we do in fact get a better, sorry, what did I, sample mean is not defined. So I don't know what I did here. I'm running it again, and for some reason it doesn't like it. So I'm going further up to find where my kernel fell asleep. There we go. Okay. And then, so there's for size 25. Let's hope that size 50 works now. Yes, it does. And we get a better bell shape. And then now the sample size is 4,000. And notice this is going to take a while, right? Because we're running through 1,000 times. We're taking a sample size of 4,000 and then finding its average. But notice that we get a very bell-shaped distribution. So this is the law of large numbers and the central limit theorem working. And again, we can use the center of this bell shape to estimate the average for the population. Okay. And you can read this sampling distribution with medians. We don't do sampling distributions with medians that often. So I'm going to stop here. And again, the big idea is that regardless of what distribution we start with, all of these sampling distributions turn out to be bell-shaped with a mean that is centered on the population mean. So we're using this distribution to estimate and produce a confidence interval for the average of the population.